Gen AI, Agentic AI kind of workshop. The whole day will be taken by Professor Anupam Purwar sir. So he will handle the session entirely today. And tomorrow's agenda is morning session. We will have Professor Saurish sir here. So he will handle the session for you. And afternoon session, Professor Sajid sir will be here. He will take care of it. And unfortunately, in this meeting, we could not have Professor Sita ma'am, and even though Professor Bharti ma'am is available, she's unable to speak right now. But these two professors are going to join us on the third day. So Professor Sita ma'am will join us in person on the third day, first half, and Professor Bharti ma'am will handle the session on the third day, second half. Okay. So this is the entire agenda that we have planned for you. So we can move on with our session. Okay. Is everyone available? Has everyone joined us, or are we waiting for someone still? Everyone has joined. Okay. So thank you, professors, for joining us. We will. You can drop off the call right now. We will be starting ahead with the first session for the day. Thank you all.
Are you all familiar with transformer architecture? Okay, encoder, decoder, everything, right? So, yeah, in the meantime, this gets fixed. Okay, I just want to get an idea. Where do we stand? Okay, in terms of your understanding. And I have been given some context, but I want to get a better picture of that. So this is how the flow of topics going to look like. This generally, when I do this is like a 12-hour workshop, but we have only today. So I will see like what all can we cover. And in fact, I would like all of you to right now give me a feedback. What are some of the things that you don't want me to miss? And what are a few things which I can skip? Okay, so here's the course outline. So have you all done any post-model quantization? Quantization, have you done? Language model quantization? Not hands-on. What type of quantization techniques are you aware of? But so that is data type you are telling, but I'm talking about quantization techniques. Then I need to cover that. Have you read about how to host language models like natively on your own? How have you used language models so far? Through APIs or by self-hosting them? APIs. For self-hosting, has anybody done self-hosting using GPUs? No, I'm talking about GPU. That is CPU. Anybody has used VLLM library? Then I need to cover 3 as well. Has anybody said vector database? Vector databases? So probably I will go light on that. Okay, so point number 4, I will go quickly on that. Are you aware of engine? Okay. 120 GB. FP32 120 GB. What about VF16? How much storage? 30. Now you have 48 GB RAM. What should we do? We have 48 GB RAM. This model is 30 billion parameters. What should we do to store this model? Quantize to int4. Right? Why should we quantize to int4? FP32 means 120 GB. One of your friends said VF16 60 GB, still more than 48. Then what are we left with? Go to int4. int4 mein how much will we need? 30 GB. Okay. So 30 GB. The verdict is clear, right? We need 30 GB in int4. So, and how much RAM we have here? 48 GB. What will you do with 18 GB? Why do we need it? Very good. See, some of you are getting it. I'm very happy. 18 GB for KV cache. Right? But are you sure 18 GB से हो जाएगा? Why would you need more? So what will you do? How will you handle that? Where is this context coming from? Where is the conversation coming from? Where are the prompts coming from? Yes, he said from the users. If you have 18 GB RAM and if it is overflowing, then sorry, you'll have to control the users. You can't have infinite number of users, right? With 18 GB RAM, right? If you would have too many users, okay, then you'll have say m number of users and then m into on. So what is why do we have to limit the number of users? Now tell me, why do you have to limit the number of users in a real life application? Limited, limited memory, and where is this memory going? KV cache and storing the model weights, right? So this is something very fundamental. We all use language models, okay, and sometimes we get rate limit error. Sometimes Claude will go down. They will say you're out of free messages. What are they doing? They are rate limiting you. They like free user है, इसको rate limit कर दो. 5 घंटे. Let's not give him any response. You have to pay for premium, right? You're not paying, they rate limit you for 5 hours. KV cache जब खाली होगा तब बात करना, right? So depending on what is your RAM that you have available, 48 GB RAM you had, okay. 30 GB तो गया weights में. 18 GB was left. But do you really think 18 GB पूरा KV cache को मिल जाएगा? It is not like that. So there will be 2-3 GBs which CUDA kernels will just consume. That is CUDA overhead. Okay, it does some state management, some graphs, CUDA graphs it creates. 2-3 GB वहां गया. कितना बचा? 15. चलो 15 बचा. अभी if you are saying कि we really need an annotator now because I'll have to keep removing this otherwise. 30 GB तो storage में चला गया. ठीक है. And that also like it will be 30 to 32 GB चला जाएगा उसमें. It's not you can just cut it at 30. 30 is the best possible number. 2 to 3 GB will go in CUDA kernels. What are you left with? Or even less. ठीक है 35 इसमें गया. 12-13 GB you are left with. अब 12-13 GB you have to manage your KV cache. So how this will impact what? You already gave the answer. Now you're going back again. Number of users. Okay. So there is a parameter called max number of sequences. That is the number of users. Max number of sequences which VLLM can support. That is what is this thing. Okay. And in fact, you will not be even left with 12 to 13 GB. Why? Because if you will run such a tight ship, and if say any of these things थोड़ा बहुत like plus minus 5% हुआ, then what will happen? What error will you get? Very famous error. Out of memory error. So how do we control that? So in case of VLLM or any language model hosting that you do, you have another parameter which is like max GPU utilization. That is generally on a safe side set to 90%. So not even left with that. You're left with some 8-9 GBs of KV cache. Okay. So for 48 GB RAM, this is the server that we can go with. G6 E4X large. You are aware of AWS. AWS offers this server. And I have also put how many conversations you can do. Given some numbers also there. We will go to that calculation now. Okay, why I have put 50 users and all that. So this is your overall diagram. I know it's not visible, so open it in your laptop. I can't help. My slides are very clear, but it is pixelating everything, the projector. Everybody can see the slides on screen on their laptop. So I will talk from the laptop, okay, for the meantime. So I have said, okay, 48 GB RAM, okay, around 18 GB goes into the weights, then some KV cache. And I also mentioned, like, if we are using a rack-based system, then you'll have to save this BGE model also, which is again 3 GB, right? So even with 48 GB RAM, it is like a very tight ship, okay, if you are running a rack-based system. Okay, and your vector database will go into the system RAM, and your code, fast API based code, it will run again in the CPU. I already told you this, right? Int 4, we'll go to int 4. Okay, and to do that, we'll use something known as one technique known as activation aware quantization, AWQ. Heard of this? No? Okay. So generally people use two type of quantization. Before AWQ came, there or techniques, okay, which will do what? They will just round off and drop the decimal places to bring it to int 4. What will happen because of that? Huge loss in accuracy. The model may lose its reasoning capabilities. Why will it lose its reasoning capabilities? The way these models work, these language models, though they may have billions of parameters, but there is a very small fraction, 1% of the parameters, which really determine their reasoning capabilities, reasoning and thinking capabilities. Now, during round off, if you ended up rounding them, what will happen? Whole reasoning capability gone. Okay. So people came up with one technique which is AWQ. And in this, what they do is, because we know that we are going to round off, drop some decimal places. So one way to sort of avoid that drop from happening is to suppose you have this parameter, which is this is an outlier parameter. This is your parameter. So many decimal places, right? And suppose we have a list of such parameters, say some 10,000 parameters, which run into so many decimal places. And if you drop them, then these are those 1%. You will lose your reasoning capabilities. So during round of what happens? Probably it may be cutting it at here. Okay. These decimal places are going away. So one way of avoiding this round off from happening is what you do is you bring the decimal place here, right? Shift the decimal place. Now round off पे कुछ होगा? Earlier the decimal place was here. What we have done, we have shifted it by 4 places. What's happening now? Anyways, it was going to keep 4 decimal places. What you did, you scale these parameters by 1e4. But now what happens to your computations? It will change the way the attention scores and everything was getting calculated, right? How do you fix this now? That you can fix it at the input level. Whatever you are multiplying here to the weights, The same thing you multiply, divide by on the input side. So because suppose your matrix calculation was going to happen w dot x, something like this. X is your input. You increase w by 4 times. This becomes 4w. Then you divide it by 4. That's what I have written here. This is inverse, right? So you change the input, you multiply input by whatever you are multiplying the weights by. You divide the input by that same factor. Now what will happen? This weight is stored and captured in its full precision. Right? You're not losing the decimal places. This is known as activation aware quantization. And this scaling, as I was saying, that you have to apply this scaling. Now, how do you determine that my scaling factor is proper? The way, right? Like to know how much scaling you should be applying. Right? So, for that, what they generally do is they use a very small data set for calibration, which helps calculate the scaling factor. Okay, so this calibration data set will be like a data set of input and output, some 128 or 256 input output pairs, and we'll iterate using different scaling factors and see if the responses are preserved in the same quality, even after I am applying quantization. You will quantize, you will multiply by the scaling factor, quantize, then pass the input through the model and see if the response is the same for those 128 questions. Okay, we keep on doing those iterations, and once we know that now my responses are as good as the actual responses which were there before quantization, I'll stop at that scaling factor. There is one more technique known as GPT-Q. Okay, uh, it is much slower than this technique, and it requires much larger calibration data set because it calculates some second order Hessian matrix, and to calculate that Hessian matrix, it needs a lot of bad data, calibration data. So that is why it is much slower. Any questions on this? Because you are not sitting here, you can't see. That is why you missed it all. Okay. I said whatever you multiply the weights by, input you divide by the same thing. So that when you do the matrix multiplication of input and the weights, you get the same value. Okay. So here I am dividing this x dash is nothing but x into inverse of whatever factor I multiplied by the scaling factor. Okay. Okay. Now let's look at the memory budget now. What will happen then? Because you already, so you have to adjust, right? You increase the parameter by some factor, right? The weights. You increase the weights by this factor, right? 10,000. You multiplied the weights by 10,000. Your output will change, right? So how do you offset that? By dividing the input by the same factor, which is 10,000. Scaling of scaling of data or the weights? Yeah. You use the same data then, but when you'll quantize, you lose 6, 7, 8, 9, right? But we don't want to use 6, 7, 8, 9. Because quantization will cut this away. We don't want to do that. Okay, so that's why. So Srivastaji is here. I think some of you are not able to see what I'm putting on the board, so this is going back and forth. They were bringing the annotation, right? Please get it quickly. Okay. I know some of you are struggling because what I'm writing on the board may not be very visible, okay, to everybody sitting at the back. That is just one factor, right? Scalar multiplication. You're not doing any matrix multiplication. It's a scalar multiplication, right? One time. So tell me, so okay. So it is just one time it happens, right? You just update the, that is just one time. Not for every input you are doing it. It's order of one. And then I'll have to open on this. Or will I have to, can I connect my laptop to this?
You will have to connect your laptop to this.
Acha, ठीक.
Through this, we can.
Acha, nice. But how will I connect my laptop to this?
Is there
इसमें C type ही है.
only C is there?
Yeah.
I think you can download. What is this? Can you download Vacom drivers?
Which driver? Okay, so as you can see here, this is how the memory utilization looks like, right? So, embedding models is taking away 2-3 GB. The model weights are taking 18 GB. Okay, KV cache, I'm saying 18 GB. Okay, and there is some VLLM overhead, or like the overhead which is for the CUDA kernels. So that is 3.5 GB. So your margin of safety is around 6.5 GB. Right, so 6 by 48 is 1 by 8, which is 12.5%. So your max GPU utilization here is 88%. Okay. Now, given that, if say you are saying that, okay, I'm going to allocate 18 GB KV cache. Now, what does this determine? We already discussed. Number of users. Right. But how many numbers of users can we support with this? We have to do some calculation, right? How will we approach it? You have 18 GB space. Number of users you have to determine. How will you approach that? Tokens per user. Okay. So give me a good guess. How many tokens per user would be there? It is a chat system. Okay. Any other guesses? On an average, how long one question and answer pair is? 1,000 tokens. Okay. Any other guesses? So yeah, 1,000 tokens is a reasonable guess. Okay. Input output मिला करके it could be input output मिला के it could be 1,000 to 2,000 tokens. Okay. Now, if it is say 1,000 or 2,000 tokens, how would we know that how much of the KV cache these tokens are consuming? If you say 1,000 tokens, okay, then that 1,000 tokens need to be converted into some memory usage, right? So that is what we are doing here, which is bytes per token. Okay, and the way it works is the 2 times the number of layers, 2 times the number of layers into the hidden dimension, and then bytes per value. V is your whatever, like whether if you it is BF16 or FP16 or FP32. Okay, if you do this, okay, it will give you like around 180 KB. Okay, 180 KB per token. What do I have to install?
Back home. WA. COM.
Yeah.
16, 60, 60 E. This driver.
This one? Drivers?
Driver. Good.
Micro S, right? Yes.
Laptop we can.
Oh, no, just time I'm installing. Okay, it's installed.
Just a minute. I've asked them to get the USB hub.
But yes, I have to open this, right? Platform center, right? No, but I will be writing here, right?
Yes, sir. Everything will be here, sir. Your screen will be here. You need not look at your laptop.
Acha, okay.
Your presentation, WebEx, everything will be visible here.
Okay. Okay. So, yeah.
Just get the USB.
Sure. So now, what have we done here? We now know that, say, per token, this much storage we are going to require, okay, which is 180 kilobyte. Could we have approached it in a different way? One token, how big is it? One token, how big is it? Uh-huh. Somebody said one token, how much storage would one token need? 1.5? 6 KB. It has few letters. Say 5 characters. One character, okay, can make some approximations, right? So if 5 characters, how much storage is required for storing 5 characters? No, I know, but I'm trying to make others think. 5 characters, how much storage will it need? Yeah. 5 characters, they are saying 20 bytes. Do you all agree? How much? Why are you going into dimensions? You're overcomplicating it. One token has 5 characters. How much those 5 characters need storage in bytes? 20 bytes. Okay. Anybody else here? 5 characters, how much storage does it need? Huh? 2 to 3 bytes. Okay. I'll come to that. Okay. So now I'm bringing a very important concept here. Okay. So you may allude to thinking that okay, there are one token has 5 characters, so then I need like 20 bytes or something like that. Suppose one character is say like FP32, it requires 4 bytes, so then 5 characters will require 20 bytes, right? It's a very enticing thought. Okay, and then you like 20 bytes लगता है अगर एक one token के लिए I have 1,000 tokens, so then कितना लगा? 20,000 bytes, right? And you say 20 KB. But is that the reality? What's really happening? After that token goes inside, what happens? When you put the token inside the language model, what happens? It generates the embedding, right? And those embeddings then pass through multiple layers. Okay. That is what is captured. The number of layers into the dimension of that embedding. Right. And then B is like your whatever. It is in 2 bytes or whatever 4 bytes. I'm just trying to explain why this formula is like that. Now you won't have to mug up this formula ever in your life. Right. So one token is entering, it is passing through multiple layers, which is your D there, L. Then one token is converted into an embedding, which is say 768 or whatever, 1048, 2048, whatever. So that is your D. Okay. And this 2 is coming from the token needs to be stored both as K and V. KV. KV cache का calculation कर रहे हैं ना? कितना KV cache लगेगा for the token? K and V is 2. That is your 2. This is your number of layers. D is your hidden dimension of embedding, and B is your whatever 4 bytes or 2 bytes. Right? Makes sense? या hallucinate किया है? सही है ना? Somebody is thinking I created these slides using AI. Yeah, I did. But and everybody is doing that because it saves time. But then the understanding needs to be very clear. Okay. So based on some approximation, it says okay 180 KB. अब 18 GB स्पेस बचा था हमारे पास केवी कैश में, राइट? 180 केबी तो एक वन टोकन ठीक है. तो अगर इफ वी मल्टीप्लाई दैट बाय 1000 टोकन्स, okay, अच्छा इस उल्टा करते हैं, like we can do it another way. So 18 KB is required and 18 GB is there. We can store 1000 tokens in the KV cache. 100,000 tokens we can store in the KV cache. Now if say one user is having 2000 tokens input plus output, then how many users can we support? 50. 2000 से divide करेंगे. If input and output is lesser, you can support more users. But then you have to make an average approximation. ठीक है, you can't design it for the outliers. ठीक है, किसी को ऐसा हैरी पॉटर ही अपलोड करना तो you can't help it. So you will do it for the average audience. कि भाई 2000 tokens लगते हैं. ठीक है. And now this is also going to give you idea why these people restrict you from uploading a very large file. एक ही यूजर पूरी केवी कैश खा जाएगा, पूरे सिस्टम को स्लो कर देगा. Well, there are guardrails for that also. Okay, so there is one concept known as chunked prefill. I'll go there. Okay, so chunked prefill avoids one malicious user downing the entire system. Okay, so I'll come to that. So here we can support 50 users. Again, we'll apply some factor of safety. We'll say नहीं भाई 40 users ही रखते हैं, ठीक है? Because there are people who may enter probably 5,000 token input output. ठीक है? Now, I think now in your mind it is very clear why, how much concurrent users can you come up with if your limit is 48 GB RAM, VRAM. Now you can do the same exercise in your organization depending on what is the instance, what is the model, right? You can design it on your own, right? So this is not something rocket science, okay? Very simple arithmetic, right? An accountant can also do that, right? If you have 48 GB RAM, you can support 40 users while you are using int4. Okay. Similarly, you can do computations, right? For any model, if it is a 70 billion parameter. So 70 billion parameter, let's do a calculation. How much VRAM would we need to store the model alone? int4 में कितना लगेगा storage? He's saying 35 GB. Anybody else? अभी ये 30B को हमने int4 में किया तो कितना लगा? 30 GB लगा ना? 70 GB चला जाएगा, right? Which type of VRAM would like which GPU would be required in that case? हाँ? हम लोग 100 GB RAM तो लगेगा, right? Right? A100 जो है it gives maximum 80 GB. You need at least two A100. Okay. Right? Now if you have to make like a decision that I am going to host a 70 billion parameter model, you know two A100 cards will be required. This is another question that comes in the interviews, okay, very frequently. कितना A100 लगेंगे? Okay. And then rest things you can do, right? Now, how much are you left for KV cache? 2 A100 लगा दिए, 160 GB, 70 GB मॉडल में गया. How much are you left with? 90 GB. और भी ओवरहेड्स हैं, as you can see, 10 GB उसमें चला जाएगा. फैक्टर ऑफ सेफ्टी भी 10 GB रखोगे या, ठीक है, कितना बचा? 70 GB बचा. Still it is a lot. Now based on that 70 GB, you can think of how many users you need to support. And you can just make this assumption कि भाई 200 kilobytes per parameter per token will be required. 200 याद रखो बस, ठीक है. उससे you can calculate 200 say if you will divide 200 into 1000 say 200 KB से divide करोगे, that will give you the max number of users, right? उसके लिए फिर अभी एक और चीज लगेगी कि you know how much is the input output going to be for one user, right? That becomes your design choice, right? If say you want very lengthy responses or very lengthy questions, you would know your business use case, right? You would know 5,000 होगा input plus output या 10,000 होगा या 500 होगा. You would know your business use case. Okay, so that information you get from your business use case is for equation say you will get maximum number of tokens that you can support in the KV cache, and that determines your concurrency or number of users or maximum number of sequences. Okay. Are all of us on the same page? Yeah. So now give me a quick check, okay. Are these things that I'm covering, was this covered anywhere else in the last 3 semesters? This concurrency and was it covered? So now you can design a system, right? How many of you are confident? Given a language model and some choice of GPU, we can provision, right? Things. Any questions? In the meantime, setup happens. Any questions?
That was true. It was increasing drastically. Complete 20 GB actually become one of them.
Yeah, 3 billion के साथ नहीं होता है. I know. Yeah, that option is there. So it is known as, I think I have covered that, but there is a way you can allow some of the KV cache to flow to CPU. Okay, one parameter is there. मुझे याद नहीं आ रहा है वो, but what it does is it slows down your system, slows down your processing, because then CPU GPU के बीच में some overflow, something like that is there. Max offload, yeah, offload needs to be true. It is slow. KV cache offloading is there. It is very slow. Do model sharding, na? FDSP, full data sharding parallel. Use that. Okay. Or there is one more framework, tensor parallel. Use FDSP. FDSP is sort of right. Full data sharding parallel. FDSP. अच्छा ओके ये अच्छा इसी से काम करेगा अच्छा ठीक है नाइस इसको तो टाइप नहीं कर सकते ना इसको ऐसे कर देता हूँ I may need whiteboard some keyboard sometime. They can see the screen. I think so there is one more thing. Okay, there is one more way. You can actually increase the number of tokens that you're handling. So for that, you can use FP8, and then that will take your max number of tokens to 200,000. Then you can support more users, right? It was 40, probably now you can support more users. Okay. But if we use FP8 KV cache, then over multi-ton conversations, you will see loss of precision. So if it is like, if you know that the conversation with the user is going to be like 2-3 conversations long in one user session is max 5 conversations, then FP8 is fine. But if it is going to be more than that, then you will lose the precision over say 50 or 100 conversations. In that case, we have to go with VF16. So again, this is guided by your business use case. So very integral to the concept of KV cache is the concept of paged attention. Somebody asked me what is paged attention. Now I'm getting into that. Okay. So generally, like, so you know about contiguous or non-contiguous memory? Okay. So what one can do is, suppose one user query comes, okay, and corresponding to that, the KV cache requirement gets stored something like this. Okay. Then another request comes, goes like this. Then another comes, we go like this. Right. So sequentially it is getting, okay. And we know from where we know the pointer, okay, like the address. Okay. So here what we have done is we have just allocated it by block by block. Now for the memory management system of the KV cache, how would it know how much space should it reserve for one request? So it makes some approximation. Okay. And what it does is it reserves some space across your 18 GB. Okay. And whenever these KB values are coming, it will store them in this order. Okay. Now, corresponding to and it would know that, okay, because I have stored it in this order 1, 2, 3, 4, 5, 6, it would know where to fetch the information from because the order is known. So that it is doing it in an order only. But the disadvantage with this sort of an order is, suppose after storing the M requirements, okay, you are left with some space which is here. Okay, let me extend this a little further. Okay. And you are also left with some space which is over here. Now, there is no way for you to utilize these pockets of spaces. Probably a smaller request may come in. Okay, and it can probably go fit here. Another smaller request may come in and it may go and fit here. But what you are doing is you are just trying to store it one after the other, okay, in a particular order, so that when you are retrieving it, you know that order and you retrieve it in that order. So this is where paged attention steps in, and it says that you don't need a particular order in which you are storing the memory or the KB values. You store it wherever you find space. Suppose it finds space here, it will store something here, and it will keep a table, okay, where it will store the pointer for this block and say the number of the block. Similarly, when another request comes, it found that, okay, it can take this entire space, okay, and it takes the pointer address of this place and puts it that entry into the table. So it can create a table like this, okay, and wherever it is finding space, whether it is here or here or here, wherever it will find the space, it will accommodate. Okay, it is not doing it in an orderly fashion. So think of it like how people stack things in warehouse. Generally in warehouse, they put the inventory wherever you find the space. Okay, and then they scan the QR code of that location and store that information in their database. Right, and when the pick is to be done, then it will show in their system, in their handheld device, that okay, you have to go and pick it from there. Then that way your utilization of space is very good. You'll try to do it in an orderly way, and say every shelf or compartment has a limited space, a well-defined space. What you will do, you may do it in order, one by one. So in that way, you will not have to maintain this table, because you know that 1 से लेकर 100 तक यहाँ है, 100 से लेकर 200 तक यहाँ है, ठीक है. But then your space utilization may not be very good. With this, even if there are pocket of spaces left here and there, what you can do is you can put those KB values there and then just log it in this table. And maintaining this table would take you few kilobytes of information. But what it ends up freeing is, and this can go into the CPU. Okay. What this helps doing is it will help you completely utilize your 18 GB of GPU RAM. Because not all the requests will be of the same size. Some will be 1000, some may be 400, some may be 200, some may be 100. So you don't need to reserve blocks for them, because if say your request is 100 tokens and you have reserved a block which is say 1000 tokens, then what will happen in that particular block? This much space is empty. You're wasting that block. So in the traditional ways, you reserve blocks of memory in the KV cache, and whenever a request is come, you dump there. But then what it leads is it leads to sort of poor utilization of the space. So paged attention does dynamic allocation of memory. Whatever is the size, it will try to put it in whichever location it finds that much memory, and just take the pointer of that and store it in a table. And that table can be stored in CPU. And when the retrieval is to be done, it will just go and look up that table and retrieve the information from there. Okay. So in that way, what happens is you are able to accommodate, you are able to fully utilize your memory, GPU memory, and you are able to support more users. Okay. So that is the concept of paged attention. And if you are using, so paged attention is like a memory management system. It's not that we are doing any calculation here. Just we are keeping a log of what information is going where. Okay. So clear? This part is clear?
That table in that CPU will lead to latency. It's every time
It's a small table. It will be like in few kilobytes.
CPU to CPU communication over.
You can store this in GPU as well, okay. But suppose you are like, no, I'm very particular. I'm not going to store in GPU because it will take few kilobytes. Then you can put it in CPU as well. Okay. But so that is why that VLLM overhead was there, because it used paged attention. So all the overhead is actually related to this. Whatever tables it is creating for memory allocation, all those things are there. Okay. So paged attention, as I said, like it's like a memory manager. That's all it is doing. It is doing memory management. It is sort of storing the KV values in fragmented locations, in different diverse locations, and keeping a track of what that location is. We're not creating blocks. That's what I said, right? This is traditional way, right? That we will create blocks, okay, compartments. But in paged attention, we don't do any of that. It can go anywhere. Wherever it will find the space, it will just push it there and take a pointer out of there and store it in this table. Now I'm coming to another concept, which is okay. So we have handled the KV cache well. Okay. This KV cache is required in which part of your processing? It is decoding. Correct. Okay. So decoding determines decoding, KV cache, paged attention, these are all linked. Okay. And the metric that is related to decoding is time per output token, which is TPOT. Right? Every additional token that you're getting in the output, how much time it is taking. It is also known as ITL, inter token latency, or TPOT. Now, decoding, we have gone into much detail. Okay, we spoke about KV cache, we talk about attention, paged attention. Now let's talk about the other thing, which is prefill. Prefill is what do we do in prefill? We calculate the KVQ matrix, right? This is the input, right? After you do the prefill, okay, the encoder, sorry, there's no encoder, sorry. First, the information comes in, it calculates all those cross attention and all those scores. So that is prefill. And once the prefill has happened, okay, we have all the attention scores. Okay, so this process is compute or memory bound? Compute bound. And this is where flash attention comes into the picture. Okay, so now I'll go into flash attention. Some of you may be feeling a little confused. Okay, don't worry, things will fall in place soon. So there are flash attention 1, 2, 3. Now 3 have come. The difference between flash attention 2 and 3 is this 3 came to support H100 like the Blackwell series of GPUs that are coming from NVIDIA. And this FA2 was to support for A100. So not much of a difference between FA2 and FA3. It is FA3 came to sort of cater to the specific hardware architectural requirements that are there for H100 GPUs. Okay, H100 is a family of GPUs from NVIDIA. A100 is also another family of GPU from NVIDIA. Okay, so during the prefill, what we do is we are doing all these big matrix calculations to calculate attention scores. Now, when we are calculating these attention scores and multiplying these matrices, it is like multi-headed, right? So for multiple attention layers, these calculations are happening. Right, so as many as layers, okay, 1, 2, 3, up to n layers, all these calculations happen. Okay, and for these multiple attention heads, okay, these computations will happen in parallel because GPUs, okay, support parallel computing. So like the entire GPU high bandwidth memory will get sort of in parallel, it will start processing all these matrix multiplications. Then then what happens? Some normalization also happens, some batch normalization, right? All those things happen. Then after that, you have some feed forward layers. So maybe there is some regularization and normalization that happens, right? So all these processes that happen, okay, in order to do all these calculations, it's not that the matrix multiplication will happen in one go. These are very big matrices. They may decompose the matrix, then sort of bring it together. Okay. So what FA2 does is to sort of do these computations, the intermediate values without FA2, they would actually go out of the GPU. Okay. And it may offload it to CPU, and then it will increase add the overhead of input output, right? In case of FA2, it uses something known as registers on GPU itself. Okay, and the intermediate values never leave the GPU, so they don't have the overhead of bringing it back to the GPU, and they do something known as kernel fusion. So say in step 1 some calculations happened, So step 1, some calculations happened, some intermediate values came. Now they have to go for say normalization in step 2. So this is the attention step and this is the normalization step. Okay. So without flash attention, it would with flash attention, what happens is it goes to registers, okay, memory registers, which are there within the GPU itself. Okay. And because these intermediate values never leave the GPU, okay, so the time that would have been spent in loading these intermediate values, that is actually saved. And because of that, your throughput, okay, or tokens per second that can be processed, that goes up. So this flash attention is something which is very specific to the prefill phase, where all these attention, normalization, regularization, and then passing to the neural network, okay, like all these steps are there, right? So the whatever intermediate states or values are there, they never leave the GPU. They always remain within the GPU. And that saves you time. And if you are saving time, then your throughput or tokens per second processed actually goes up. So I have spoken about flash attention, but it does not solve that real life problem. When a single user comes with some 10,000 token request, we were on an average we notice that it is 2,000, but some users comes with 10,000 and other comes with 100,000. Now what will happen? These requests also will go into the prefill phase, right? And well, whatever GPU bandwidth that you have, these calculations like these, this is a user N, this is a user M. They will occupy that space, and the remaining users for which the calculations were already happening. Okay. The chances are it may slow it down. Okay. So for say these users, prefill has happened and it has gone to the decoding phase. Now, and for these users, 5, 6, 7, 8, suppose it is still in the prefill phase only. So for these users anyways waiting, okay. But for these 4 users, decoding had already started. They had started some tokens coming out. But then these users N and M came into the picture. Okay, and they entered something which is this big. So because these users have pushed something very, very large, okay, so think of it like this. Suppose there is a pipe, water is flowing. Okay. And you try to insert a very big object into that. It was okay if you are putting small mud particles. They were anyways getting through. Okay. But there is a specific diameter of the pipe, right? Now if you put a very big object, what will happen? Those smaller mud particles that were coming out, they may get choked. If say the object that you are putting is as the same diameter as the pipe, सब कुछ रोक देगा वो, right? Till you really force it out, it will stop everything. Something similar happens here as well. Now these users which have inserted these many tokens, if you let them come inside, what will happen? It will, your GPU तो supports parallel processing ना, कहेगा आ जाओ ठीक है, let's start working. Okay. If it has not really touched the 100% GPU utilization, it will take that. But because these calculations would be happening, it will slow down the decoding for every other user. So then what they will say, they will see some stutter. अभी तक तो decode हो रहा था, Now suddenly the inter-token latency or teapot goes up. So somebody ended up putting a very large request. Okay. Now, in that way, what would suffer? Your teapot will suffer, your concurrency will also suffer, because now these users will stop seeing any output. So their time per output, token, teapot, and the concurrency. अगर कुछ नहीं आ रहा है तो then concurrency is suffered, right? Now no response is coming. So if very big requests come into the picture, then your time per output token goes up, your concurrency takes a hit. So to sort of alleviate this problem, there is a concept of chunked prefill. Okay. So now what chunked prefill does is, whatever user requests are coming, if you say chunked prefill is true, and the chunked prefill is one user setting, then there is one more thing which is here I can't write. Acha, what is the time?
11 o'clock.
Acha, okay, you have to take a break. Okay, I'll just finish this and
Finish.
this concept. We'll take a break soon, okay? So just let this concept be completed. So we said chunked prefill is true. There is another parameter which is max sequence size. Now, if you have defined this to be say 1000 tokens, okay, and there is another parameter which is maximum number of batches. Say this is 40. This is like your concurrent users, right? Maximum number of batches or maximum number of sequences. This was 40. This we already derived. Okay, and the chunk size, max chunk size, if it is say kept as 2000 tokens. Okay. Chunked prefill is on, max chunk size is on. Max number of batches we already defined, right? Now what it will do is, if the user is putting 10,000 or anything more than this, and chunked prefill is on and max chunk size is 2000, it will break this request into 5 chunks of 2000. And if it is not 100% GPU utilization, there is still space. For that nth user, it will only take 2000 tokens inside. Everything else, it will say, wait, I'm not going to touch it. Say some other user comes M, and that user puts 50,000 tokens. Uska bhi ye 2000 token lega, and it will break it into 25 such chunks. It will say, wait, so this is your VLLM queue. Your queue size will go up, 2 up. The 2 users are waiting now. Now what this saves you from is, because these people were trying to get too much out of the system, they will have to wait. Right? You have to be fair to everybody, right? So these users will wait, and because it does not overload the system. Now any user will not be able to push at one time more than 2000 tokens. Right? So I was giving the analogy that, okay, somebody is trying to push a very big object into the pipe. Now even if somebody is trying, first it will get cut into smaller chunks. And now it becomes like the input becomes like the same particle size for all the users. So no choking will happen. So your inter-token latency or teapot will not suffer even if somebody ends up putting something very large. Okay, so I'll stop here. I've been told that there is a break. Okay. But yeah, I think we have put some good foundation. Okay, yes, these will be shared. This recording will also be shared with the students. So you'll have everything. Okay, so I was saying that with maximum batch size per user, so if it is 2000 tokens and chunk prefill being true, you will be able to limit a user from taking exorbitant space. Let's look at something else. So I'll quickly go over this. So there are open source embedding models, like you have this BG, and then you have closed source embeddings model as well, like the ones from OpenAI. For open source embedding models, then you'll have to sort of reserve the space in your VRAM. Right, 2-3 GB we ended up reserving because these models are also big, and they are generally stored in full precision. Nobody quantizes embeddings model. At least I haven't heard of that. Uh, the like good part about using your open source embeddings model is like all the embeddings, all the data remains within your own premise. You don't have to send it to outside. Okay, so if privacy and security of data is a concern, then it is better to use self-hosted embedding model. You can fine tune these embeddings model as well. Have you so anybody has idea like what is an embeddings model? How does it work or how is it trained? Because this part you may be aware, okay, that make just call the tokenizer and then the embeddings model and it gives you the embedding. But do you know how an embeddings model is actually trained? In an NLP they covered it, right? Megahertz, TF-IDF. TF-IDF is not embeddings, just a statistical approach. So I'll just quickly give you an overview of it. We can skip this also. You can tell me like if you don't want this. So the way an embeddings model would work is first it is going to do some feature extraction. There will be some layers which will do some feature extraction. Okay, and then there will be few more layers of neurons which are going to finally project it into a particular number of dimensions. Okay, so and the way this works is it calculates the cross entropy loss. Okay, so the way it would work is similar words they need to get projected in the in a cluster together. Okay, and so So this will be your output embedding, and here you will have like your word get into, okay, and it will be converted into token IDs, okay, and token ID may be a list or serial of numbers, okay, and there are different tokenizers, right? Tokenization you all understand, right? If not, I can show something quickly. There's one tokenizer. So look at this. This is a nice application. Now, if I add here, now you see what has happened here. It is color coded. This is one token in yellow. Okay, is also another token in green. Okay, but what happened to my name? It has broken it into three different tokens. Okay, and then you can see the token IDs also against it. Right, so these are token IDs. So there are different algorithms for converting these words into token. For example, byte pair encoding is there, and they convert the words into these token IDs, and these token IDs are then converted into embeddings using embeddings model. So embeddings model is so this is your output, the one that you are seeing in green, and this neural network through which the words are getting processed. This is your embeddings model. So nothing but a layer of neural neurons. Okay, and the output, whatever you get in the output, after you have trained to minimize this cross entropy loss or contrastive loss. Okay, whatever network is left with you, that is your embeddings model. Okay, and you put the words into this, and then you get those embeddings out of it. Okay, so it is just a very dense neural network. You can think of like that. Again, what would happen after you would have done this training? After it has done you have done the training, words which are similar. Okay, so if this is, I'm projecting this in 2 dimensions, then these words which are similar will get into one cluster, and these will get into some other cluster. Okay, and the way this would work is, if you will do boy minus girl, and if you will do, say, father minus mother, it will be, you can write it like this, the way these vectors would be. So grandpa minus grandma is equal to boy minus girl, or is equal to man minus woman. These type of relations will come between these words. Okay, after you converted them into embeddings. Okay, so just I was trying to give you a quick overview. I think you already know this. So there are, yeah, so and again, like these embeddings model also, they have like the output embeddings that come out of them, they have different size. So older embeddings model used to have they can only consume very small number of tokens, for example 512. Okay, no, but the newer models, they can, newer embeddings model, they can concurrently process a lot of text. So OpenAI has this text embedding, 3 large, then there are Gemini embeddings, then there are embeddings from Cohere. Okay, so these are like some of the closed source models, and they charge you on token basis. Okay, and you can't fine tune them. You cannot adapt them to your particular domain. But like time to make it live or time to market is very low for this because it's just an API call that you are making, and they have very good large chunk context windows, so you can at the same time create embeddings for 8,000 to 32,000 tokens. Yeah, so this is just a comparison. Okay, open source versus closed source embeddings. Okay, go open source if your data is highly sensitive and you need to fine tune. Go closed source if you want to get quickly to the production. I think this part also most of you would be aware. So, if you use a vector database like Quadrant, uh, it creates these different index graphs, and why should we be using these vector database is because one thing that they do is they shard your information. Okay, uh, and they support a lot of metadata as well. Okay, and they do something known as quantization. So by sharding, what they do is, if say you have lots of documents, then they will sort of break it into different chunks and spread it across different vCPUs. Okay, so you can think of each vCPU as a worker. Okay, so if your instance is having 32 vCPUs or 64 vCPUs, then each of the vCPU can be handling one shard at one time. Okay, so it brings in advantages related to parallelization. Another thing is they are able to capture a lot of metadata. For example, keywords or maybe topic of that particular chunk that you're storing in the vector database. I'll get into that in more detail. And the other thing is they quantize the information when they store it. So if suppose to think of quantization, so suppose an embedding is 4096 long. Okay, so it has these many decimal places. Okay. When you do quantization, okay, what you do is you may break this into different chunks. Say you break it into chunks of 128. I think this will be 128 into. Can somebody do this calculation? What would this be? 4096 by 128. Sorry, 32. Okay. So your embedding is broken into. Okay, let me come to this in a while later. Okay, let me first explain quantization in the context of vector database. Okay. So think of that. Suppose you have to come up with wardrobe for a celebrity. Person is going to wear some shoes, put some hat, okay, some goggles, uh, some perfume, some jacket, right? So many things. Now, if you start writing about that, probably you can fill 2-3 pages, right? Celebrate but instead of that, what you do is, suppose you have a catalog. Okay, so in this catalog, suppose there are 16 pages. So one is related to shoes, another is related to hat, another is related to shirt, another is related to pant, another is related to jacket, another is related to hat, something like this. And in this, each of this page, you have like some 256 say options for each of this. Now what you can do is, so this is a catalog of 16 pages. Okay. And and there are 256 choices for shirt, 256 for hat, something like this. And instead of really writing 2-3 pages long description of the person's wardrobe, what you do is you pick one number, serial number from each of this page. Okay, so 2, this is 4, this is 8, this is a 10, this is 11, and this is say 255. Right. So similarly, you can have some 16 values. Okay, this is 9, this is say 0, something like this. Okay, now so earlier what you were going to do is you were probably going to write multiple sentences, and they may have gone into 1 page or 2 page depending on the detailing. Okay, but now what we have done here, and if you would have converted that into an embedding, right, it would have so many tokens, and then you can think of you'll have stored so many embeddings corresponding to each token. But here what you have done is you've converted that into just 16 numbers, right? And still you are able to capture all the details. So suppose that information would have been say 5,000 tokens long, which is like 1 page. You have compressed that to 16 values, right? And even if you are storing these 16 values in full precision, first of all, you don't need to store it in full precision because this is all integer. You can, for this also the data type can be int4, right? Because you don't need any decimal places. And so this could be like 16 bytes, right? 1 byte each for each of this. This is like 16 bytes, okay. Whereas if you would have like a 5,000 token long or even 1,000 token long description of the wardrobe, it would have been so much information. This is a simple example of how quantization works. Similarly, when we talk about a vector database, uh, instead of really storing each embedding at full precision, what it does is it does splice quantization there. Okay. And for the information that is contained in that vector database, so it keeps creating some isolated clusters. It will create multiple isolated clusters. Okay. And for each cluster, it will find out the centroid. Okay. So suppose here we have say 256 clusters. And for each cluster, now you have centroids. So you have 256 centroids. Right. Now, when you will sort of project the embeddings in the n-dimensional space, some embeddings will fall in this cluster 1. Some may fall in this cluster, some may fall in this. Now, when you break your document into multiple chunks, right? First step is you break it into chunks, right? Everybody, you break it into chunks. Now, probably first chunk may be close to this cluster. Okay. So it may be somewhere here, like if you will really draw a vector of that. This is, I'm just, for the sake of simplicity, I'm doing it in 2D. I can't do 3D, right? So one of the chunk is lying in this cluster. Another chunk may lie in some other cluster. Another may lie in this cluster. Right? So what we can do here is in terms of compressing this information.
Breaking into chunks and in different cluster, will it not lose the context of the complete document?
Yeah, so we lose precision in that. We do lose precision in that, but on the other hand, it saves a lot of memory. Okay, so that happens. That does happen. You lose context, but it saves a lot of memory. Okay, and your retrieval also becomes very fast.
Then it may hallucinate based on the.
Yeah, so there is something that I'm going to come to that. Okay, what do we do to sort of? Yeah, that is another thing. Yeah, we do overlapping of chunks, but what he is saying is like if I am mapping these chunks to different clusters, okay, and then what I am going to store is I am going to store for each chunk. I am going to then store the centroid. If say I broke that document into say 16 chunks, then I will not be storing the actual embedding. What I will be storing is that this chunk. So chunk 1 belongs to this cluster 1, chunk 2 belongs to this cluster. So I have 256 clusters, right? So I would have 256 values here. Now your one chunk may lead to an embedding which will be 4096. Okay, this is C256. So I would have an embedding of a document or a chunk which is 24096. I brought it down to 256. So this is quantization that operates at the vector database level. And of course, like you are far away from the centroid, you are losing that precision. But what are you trading it for? Speed and memory. You are able to store it in much lesser memory because you will store 4096 values. It will require too much space. But now you have quantized it to the centroids. And see, even if you look at the number of centroids, clusters, it is a lot actually, 256 clusters. And if you look at now this 256 is a number you can always change. Right? It's a configurable parameter in your vector database. You can make it 4096,
Yes.
you can make it 5000, you can make it 8000, depending on your use case. Now, if you know that there's too much diversity in your information,
It will improve the precision.
it will improve the precision. Then there will be more centroids. Okay. And then it will come like every document will come, chunk will come closer to the actual centroid. Okay. So if I make this 512, then what may happen? This may start coming here. Okay. It will come closer to the centroid. But then your memory requirement will go up. Okay. And your speed of retrieval will also go up. No, so now when the query comes in, right, what you do is now, depending on how big the query is, you may have to break it into chunks or you may not have to break it into chunks. Okay. Generally, queries are not very long. Right. So queries generally, whatever is the query, you keep it in full precision. The embedding, you keep it in full precision. And suppose this C1 to C256 was your one document, right? One document chunk. It was one chunk, right? So what you will do is, once your query comes, okay, it may be belonging to, it may be closer to say some of the clusters, say 2, 4, and 3. 3 clusters it is close to. Okay, because here it is in the query is in full precision. So you will know that okay, the query is actually okay.
We are not breaking query into chunks now.
Query we are not breaking to chunk. Query we are not breaking to chunk. Okay. So we may suppose the query it is closer to this cluster. Okay. Or this is very close actually. Suppose it is coming somewhere like this. So it is close to which all clusters? 3, 4, and 6. These are the 3 clusters it is close to. Okay. Suppose it is here. Okay. The actual vector of this query is somewhere here. Okay. So it is equidistant to these 3 centroids. C3, C4, and C6. So now in terms of retrieving it, what it will do, it will pick all the chunks which have C3, C4, C6, which have those centroids in them. Right. So now your retrieval also becomes very fast. I'm oversimplifying a little bit just to give you a flavor of how retrieval is also faster here. Okay, you can go and look up at more detail. But because a query is generally small, it is not really chunkable, and you store it in full precision. So you have its embedding and you see what all clusters it is close to. Whichever documents have those clusters centroid content, you retrieve them. So now this may lead to some loss of precision definitely. But now what happens is, so you may end up picking some false positives also. That's why I'm saying false precision is low. But it will ensure that your recall is high. So you get all the true positives, but at a cost of some false positives. The recall may be high, but here the precision may be low. So generally this vector data based retrieval, it is a fast process. Okay, so converting it to an embedding may take 20 to 30 milliseconds. This is the embedding time. Retrieval may take 10 to 15 milliseconds from vector database. Okay, and I will help you remember this. Okay, then comes your generation from LLM. This will be 200 to 300 milliseconds. Okay, and there is one more step which I'm not sure if you are aware of, which is re-ranking. Have you heard of re-ranking? In case of RAG-based systems, have you heard of re-ranking? How many of you know about re-ranking? No. That is retrieval only. So in re-ranking generally takes 100 to 150 milliseconds.
Like 2-3 outputs are generated and based on that is ranked like.
Okay, let me go ahead there. Okay. So you in the first step, which is retrieval, what you did is you retrieved say 100 chunks. You know there are false positive in this, right? Because the way we stored and then retrieved the information, there may be false positives. And out of these 100 chunks, you know only 20 may be of interest to me. Other 80 may not have very high relevance. So you pass this through re-ranker. Okay. And this re-ranking, what it will do, it will calculate scores between the query and these 100 chunks. And for each chunk, it will calculate a score, similarity score, and then rank order those chunks. Depending on how much is your threshold, if your threshold is 5 or 10, it will give you the top 5 or top 10 chunks. So what this will do is, it will remove the false positive. Now you are left with chunks which have high resonance with your query. Okay. And yeah, this step takes more time. which is 100 to 150 millisecond, but it is always anyways lower than the time it takes for LLM to generate the response, which may be between 300 to 500 millisecond, right? So retrieval happened in 10 to 15 millisecond. Re-ranking happened in 100 to 150 milliseconds, almost order of 10, right? No, no, अभी LLM तो आया ही नहीं है ना, अभी तो अब ये जो 5 या 10 है, this will go into language model. So there are re-rankers, okay. So there is one re-ranker that Cohere provides, okay, and similarly covered that. The re-ranking is not there in these slides. Yeah, so there is one re-ranker which Cohere provides. Similarly, there is one more re-ranker which this comes from Alibaba. These so, Cohere re-ranking is sort of paid. It happens through an API. Okay, and the one the PG re-ranker which is there, we can look up those names. So, yeah, so there's Qwen 3 re-ranker, okay, and not able to scroll this. This is Cohere re-ranker, then there is ByBG re-ranker. ByBG ranker is open source. Okay. So you can use these re-rankers, okay, and it will because it improves the precision, the hallucination will go down, quality of responses will go up, okay, and now because you are only consuming the highest quality context token, so your token consumption cost will also go down because passing through a language model is a costly operation, right? So if you are really building this type of any sort of a rack pipeline, then use this type of an approach: vector database followed by re-ranking. This is standard, very standard. What? Let me not get into the algorithm of that, okay? But you can go and look into that. I'm not sure about that. If that re-ranking and this are same, because generally, TF-Tech is I think generally used for traditional ML or NLP. I'm not sure if it has the semantic based. Maybe, but I'm not aware. I have never used hashtag. Okay, so let me now go to. So I think vector database is covered. Okay. Now, suppose you are building this agent. Okay, big system. Okay, you have accounted for concurrency. You have accounted for uh, latency. Okay, and everything is there. Okay, but you need a way to monitor this system, right? So what are some of those metrics that you are going to monitor? So I think I already mentioned these things. So one is number of requests waiting. If you are using chunked prefill and two big users came in, then those two users will go into the queue. This is that metric. Okay, then how much is the GPU usage? Right, we said we left some memory buffer, safety buffer, margin of safety. We'll generally keep it 0.9, and if it exceeds that, then we'll alert a trigger. Okay. Then I spoke about time to first token. Okay. Then hardware VRAM utilization, like absolute. Okay, like how many GBs are we consuming? Okay, and what is the search time it is taking to make one search in the quadrant vector database? So depending on your use case or you may put some thresholds. Okay, and these metrics are generally captured in real time. Okay, and you can put some thresholds and then you can get some alerts based on those thresholds. Okay, so these 5 metrics cover all the things. Okay, like your GPU, your vector database, and the performance that we are getting on the user side. Okay, we can also add teapot to it, the time per output token. Yeah, it's just the diagram for the same thing. What I'm showing here is you can have these metrics collected by Prometheus scraper. Okay, and then route them to Grafana, which is an open source package for dashboarding. Okay, so this is your application layer where your language model is running, your quad vector database is running. You are covering these metrics. Okay, calculating these metrics and then passing it to Prometheus. Okay, so Prometheus is actually scraping this information. Okay, it will scrape it from the logs and then you can plot them using Grafana. So Prometheus is again open source library which provides endpoints, metrics endpoints. Okay, and collects them in real time. And it can also calculate like the number of active users and the number of users waiting. Okay, everything it can sort of pull. Okay, so it think of it as a wrapper which is monitoring your entire agent, the application layer, and pulling these numbers. Okay, and then you can put these metrics into Grafana, which is a dashboarding solution. I think I already covered all this, so we can skip this. Right, I spoke about this dashboard that you can set, right? No, you can set those thresholds in Grafana. So you'll get a dashboard. It will give you a UI. You can put those numbers there. That for this metric, when should I get an alert? And you can organize this your dashboard into these 4 tiles. Okay, and then put those metrics in that across those different tiles. So if you know that you can actually sustain 40 users, and you see that for the last 1 week or so, you are seeing like 20 users are always waiting in the queue, right? Then 20 is a very big number because you designed it for supporting 40 users, and 20 users you are seeing in waiting, you are getting this alert for entire 1 week. Then it means your system is really under designed. You should not be getting those many alerts. You need to probably design the system for 80 users or 60 users, right? Okay, and uh, suppose you are seeing 2 things. Okay, like concurrency is also high and time to first token is also high. Now, time to first token is sort of determined by how quickly the prefill process happens, right? So probably the prefill is taking a lot of time, and that may be happening because you really don't have enough CPU RAM to do all those computations. So now so to reduce TTFT, probably you'll have to either reduce the size of the model, okay, or increase the VRAM. So if 2 things are actually going, 2 alarms are coming again and again, so TTFT and number of users waiting is coming again and again, then it is a clear sign that your system is under designed. If one metric is going up, it's fine, means something, some config you can change. Okay. But if two or more metrics are coming flagged again and again, then it means time to redesign the system. It's highly under designed. This you all know. Okay. Now I'm getting into the Kubernetes part of this. Okay. So if say we have to design the system end to end, where you are embedding, you're retrieving, generating, and then streaming the response. All these things are happening. Okay. Then how do we design it as a service? So how many of you are aware of Kubernetes? Have you used Kubernetes? No? Huh? Docker image, okay. Docker image, you all know? Okay. So let me, before I get into this design actually. So actually in the afternoon session, we have this entire exercise, okay, where I'm going to give you the entire code package. So you will be able to see all these things. These are nothing but snippets from that code package. Okay. So I will take 30 minutes to just explain you how does Kubernetes work. Okay. And why do we need it? By the way, like what is, like, all of you are from Tata Motors. So are you all working in their like some information systems division, or like what is the background of this?
Different department.
Oh, okay. So are we? Sorry. Oh, okay.
Operations, quality, all those departments.
Okay. Okay. So how many of you are from manufacturing and operations? A large number. So it means uh, so far, like the way I have covered, like were things making sense? Okay, so then okay, so we'll keep it simple in the same style. So when we are designing a service, what we generally see, some input is coming from user, then you are getting some output. Okay. It may so happen in a real service there may be 100 or more concurrent users, right? Now, when you run a code on your terminal, you are the only user who's giving input, right? And you are getting output. So it is simple, right? But now, if say 100 users are there, what does really happen when there are 100 users? Have you thought of that? Is this the only one code that is running, and then every user is hitting that code? What does happen? Sorry. Okay, we are talking about some attack. Okay, DDoS attack. Let's not go there. Okay, like I'm saying, this code is running continuously. Okay, and
Pipelines are created and then each individual user's input is taken separately and processed parallelly.
So then what does that mean? Is there only one copy of code that is running if 100 users are being served? What happens according to you?
Same code copied means different pipelines are there. So model is same but running in a different output.
So this code you created, it is running fine in your laptop. Okay, but now you want to support 100 users. So we have a very good amount of VRAM, all those is there. Don't worry about that. Okay. So you have 1000 GBs of VRAM, so you can support 100 users easily. Okay, and it's just a 30 billion parameter model. Now, if say 100 users are coming, okay, will there be multiple copies of code or just one copy of code that is running? Uh, so you know that, okay, but I'm trying to make others think about it. But for application, it is indifferent, right? You're hitting the server, okay. The server is the same. Input maybe few tokens, okay, or text. Right. So what happens is, so there is something known as GUnicorn. It is a Python server. Okay, and what GUnicorn does is it creates multiple workers. Okay, and these workers will spin up multiple processes. Okay, now if your code is written in Python, there is something called grid interlock. So this said, okay, you can only one thread, okay, at a time. So then how will we support so many users? So that is where GUnicorns comes into the picture. What it does is, if say you are specifying 4 workers, so each worker will spin up separate processes. Again, these processes are nothing but one copy of code running independently. So GUnicorn handles that for you. Okay, you don't have to do anything here. If you specify the number of workers, it will accordingly have 4 workers, and these workers will then manage these processes. Now, where are these? If I have 100 users and I have 4 workers, then each worker will have 25 processes running. And we have, if you go and look at EC2 instance or anything, what does Tata Motors use like as a stack? Azure, GCP, AWS, what do they use? EC2 instance, right? You all are aware. So EC2 instance में there is specification number of vCPUs. होता है ना उसमें? Are you aware? EC2 instance? नहीं. So when you look at EC2 instance, it will have like 2 cores तो सुना होगा, right? कितने cores होते हैं? 4 core, 8 core, so similar, ठीक है? So it will run these processes across these different vCPUs. And one vCPU might be running 2 processes. Maybe there may be 2 threads that are running. Okay. So this is at the GUnicorn level, okay, that it will create these workers. So workers are like, you can think of worker as waiters. Okay. Go to a restaurant, there may be 5-6 waiters, right? हर टेबल के लिए 50 tables है, there may be 10 waiters, right? ऐसे ही होता है ना? है नहीं कि like 50 tables और 50 waiters तो नहीं होता ना? So there may be few waiters, and these waiters will go and tell somebody in the kitchen, right? Kitchen में ज़्यादा लोग होंगे. If number of waiters is 10 in kitchen, there may be 100 people, or maybe 50 people at least who are or at least 30 people who are cooking. 2-3 times तो होगा अंदर kitchen में strength if there are 10 waiters. ठीक है. So these people will then do those cooking and all that, right? And again, like say somebody's now थाली का ऑर्डर आया यार, ठीक है, तो ऐसा तो है नहीं कि like if that thali requires 4 or 5 different things to be cooked, ऐसा तो होगा नहीं कि like say some one person say these 5 people will be put together कि नहीं अभी ये थाली का ना बाहर आ जाओ, ठीक है, सब कुछ छोड़ दो, केवल यही करो अभी, ऐसा तो नहीं होगा. They may be having some other work. Once they will get free from it, they will start working on this thing. ठीक है. For example, थाली requires चपाती, ठीक है, तो जो चपाती बना रहा होगा वो चपाती ही बना रहा होगा, बट ऐसा नहीं केवल ही इज मेकिंग चपाती फॉर दिस थाली, वो तो बना रहा है वो तो, ठीक है, ही इज मेकिंग इट इन बैचेस, ठीक है. तो जो उसके बाद पेंडिंग थाली है उसने जब बना करके उसमें दे दिया तो ही विल फिल रिप्लेनिश दिस वन, राइट. So all these processes might be running asynchronously, right? If somebody, one guy is making dal and other guy is making say roti, ठीक है, these guys will work asynchronously. ऐसा वेट नहीं करेंगे कि ठीक है जब रोटी हो जाएगी तभी मैं दाल उसमें डालूंगा या बनाऊंगा. नॉट लाइक दैट, राइट? उसका रेडी हो गया, ही हैज इट रेडी इन हिज ओन पॉट, ठीक है, इसकी रोटी बन गई तो उसने उसको बना करके इन हिज ओन बॉक्स, ठीक है. सो ऑल दीज वर्क, पीपल वर्क इंडिपेंडेंटली. So similarly, like when we spin up these processes, okay, then even if there is a sequential nature, the first step is a retrieval, another step is generation, okay, these are like separate processes, right? तो क्या होगा उसी कोड के अंदर there will be different functions that are getting called, right? Now it may so happen, in case of rack pipeline it is very sequential in nature, but suppose it is retrieving the information from vector database, at the same time it has to scrape the information from internet. Two separate functions. You can run both those functions independently, right? You don't have to wait कि पहले retrieval vector database हो जाएगा, then only I will go and search on internet. Both the things can run independently, and then that information can then go to re-ranker, right? So these two functions can run asynchronously. So when you are having these different processes or different copies of code, okay, what can happen is all the functions within that copy of code can run, you can define them to run asynchronously. Some functions which can operate asynchronously, you will define them to run asynchronously. And some functions which have to be chained together, कि जब ये हो जाएगा तभी इसको मैं कॉल कर सकता हूँ, ठीक है. You need not define that, okay, it means because that function itself will not get called, right, till the input is available for that. So those things will be chained and those some things will be asynchronous. Okay. So those things happen at the processor level, so like these vCPU level. Okay. Now there is something more okay here. So you have your G Unicorn server, which is a Python server. अभी इसको ये पता है कि मेरे को how to run my Python code. तो ना उसको आता है, ठीक है, but it does not know how to really handle so much traffic that is coming from the internet. ठीक है. Suppose your system you have provisioned only for 100 users, ठीक है, and उसके हिसाब से you have defined the number of workers, but say 10,000 users come at one time. अब क्या करें? ये क्या करेगा ये यूनिकॉर्न? What will it do? नंबर ऑफ वर्कर्स को बढ़ा नहीं सकता, ठीक है. There have to be another gatekeeper who will ensure कि भाई यूनिकॉर्न का तो मुझे पता है 4 वर्कर्स ही हैं, वो 4 वर्कर्स जो है ये चीज वर्कर कैन सपोर्ट 25 यूजर्स. Then somebody have to put this in queue. ठीक है. So that is the job of another construct which is known as Nginx. सबसे पहले Nginx आता है, फिर you have G Unicorn, and then you have your workers, and below your workers you have your code copies that are running. तो Nginx क्या करता है? अभी like 10,000 users come, ठीक है. What it will do is वो उसको पता है कि यहाँ की सिस्टम की लिमिट 100 है, ठीक है, तो बाकी को क्या करेगा? इट कैन पुट देम इन क्यू, ठीक है. और अगर ऐसा हो रहा है कि लाइक and if it does not put in the queue, then you get something like server crash हो गया, ठीक है, 404 error है, कुछ error आ रहा है 403, ठीक है. So for that not to happen, you use something known as Nginx, ठीक है. बट अभी ये भी करना है ना, you have to keep these users also engaged. मतलब ये जो नेटवर्क के जो सिग्नल्स आ रहे हैं, ठीक है, ठीक है, you have to have all these connections, you have to keep those connections right. नहीं तो क्या होगा? कनेक्शन ही नहीं बचा, ठीक है, ठीक है, तो देन क्या होगा कि यूजर विल जस्ट स्टॉप, कहेगा ये पेज ही लोड नहीं हो रहा, तो छोड़ो, बंद करो, जाओ, ठीक है. So Nginx will ensure कि these people remain in queue. कुछ उनको जो है एक default page जो है उनको serve हो जाएगा, but they will not really be able to start chatting or typing. ठीक है, but the page will load and it may be like that. ठीक है. So these connections it will ensure that those connections remain. Another thing it does is most of your secure websites have HTTPS. ठीक है, that is encrypted traffic. वो उसको decrypt करके so that a unicorn can actually process it. ठीक है, वो उसका decryption भी करता है. ठीक है. Another thing that it does is so it checks for SSL certificate. ठीक है, कि जहां से from whatever जो भी लाइक यूआरएल बंदे ने टाइप किया है, ठीक है, ठीक है, कि उसमें whether he is typing HTTPS or HTTP. HTTP is considered insecure, right? So whether HTTPS is being used or not, it checks that as well. Okay. And it maintains all these connections. It maintains all these users in queue. It may also so happen that for one user the internet may be very slow. ठीक है, ऐसा तो है नहीं कि अब इंटरनेट स्लो है तो उसका इनपुट जो है धीरे धीरे आ रहा है, धीरे धीरे वो टाइप कर रहा है, बफर होके धीरे धीरे आ रहा है. तो ऐसा तो कर नहीं सकते कि वील कीप लाइक सम प्रोसेसेस जस्ट एंगेज्ड. ओके, वन प्रोसेस इज एंगेज फॉर दैट यूजर, राइट. एक यूजर है जिसका सब कुछ बहुत स्लो आ रहा है. ठीक है, तो वी कांट डू के लाइक एक जो है मेरा प्रोसेस पूरे टाइम उसके लिए सॉर्ट ऑफ इट इज सॉर्ट ऑफ ब्लॉक्ड फॉर ऑल द टाइम. ठीक है, सो व्हाट इट विल डू इज इट विल सॉर्ट ऑफ डू बफरिंग कि भाई जब तक it define, so there are thresholds that you can define and you can say कि भाई जब तक I will not have this much input from the user, I will not let my process run. ठीक है, जब तक I have this till I don't have this much streaming information from the user, I will not engage my processor here. ठीक है, otherwise this processor will get choked. ठीक है, so it does all that. Nginx does all that, but it still makes sure that connections remain. ठीक है, some people may try to open same application from multiple tabs, the same browser or from different browsers, but IP would be the same. It tracks that also. Okay, this user is not trying to overload the system multiple times. Okay, so all those things are taken care by Nginx. So it is like a security guard. ठीक है, होता है ना, like when you go to a restaurant and you have to sometimes wait in the queue. ठीक है, but it is, but if there is suppose no security guard, people will just rush in and then just it will be a mess. Right, so somebody keeps them engaged. Okay, this is your token number, you wait here. Okay, and of course we as users, when we are interacting with these applications, we don't see those things. Okay, so there are some codes that internally get shared, okay, between your browser and the server. Okay, and then you remain in the queue. Okay, and they will serve you a default page and that is what you will be seeing. Guardrail is at a prompt level. Are you talking about prompt guardrails? If that happens at के input आ गया है, ठीक है, it is hitting the language model, but it will first check what should whether it should really get into the language model or not. So that is a separate thing. Means the process is already. So now you have passed through all this, okay, and you have put some malicious prompt, okay, which will do some tool calling, and उस tool calling से जो input आएगा, ठीक है, that may be say abusive in nature, and then LLM is forced to now consume that and generate a response. ठीक है, so that happens at a sort of a prompt level just before the language model. So all this is already running, means so people can secure the application from all this, right? Multiple users coming from the same IP, but now that user has made a connection, now it is chatting something, and उसमें chat में it is giving an instruction कि ignore everything and do this. ठीक है, so that is known as DAN attack, do anything attack. अब user ऐसा कह रहा है language model को ignore everything and now give me answer to this. ठीक है, So then it will be checked by the language model itself, okay, in its system prompt. ये system prompt में कुछ, there are two things, there is system prompt, there is user prompt, ठीक है. तो system prompt में वो catch कर लेगा कि ये तो है, this is a do an attack, so I should not listen to what user is saying. Okay, so that is prompt guardrail, that's a separate topic. So what we are going to actually do in the afternoon session, what is the time now?
45.
12:45. Okay. So I have created a code package. It's on Git. You can go and clone it. Okay. So and I need to explain about containers and pods as well. Yeah, that is so. Okay, let me use the next 15 minutes for that. This is related to deployment, Kubernetes. This is related to general deployment. Okay, this is all backend engineering. So really making real life agents is not just about writing a prompt. There are too many things which are involved. So you have to understand all the traditional software engineering constructs very well. Okay. So now what happens is once you have, so what I'm making here is a pod. Okay. So suppose you have a cloud computer. Okay. And in that cloud computer, you have multiple vCPUs. Okay. And as I was saying that, okay, like multiple vCPUs means multiple copies of code that you can run, right, across multiple vCPUs. So you can have, depending on what is the number of concurrent users you have defined. Okay, suppose you have defined concurrent users to be 5. So you can have 5 pods. Okay, and in each pod, the same copy of code will be running. Okay, and you can have some auto scaling in this. So like, agar the number of users become 10, then I will scale it to 10. So my minimum number of pods is 5, and maximum it will scale up to 10. Okay, so this is known as replica. You will create more replicas. Okay, this is your min replica and this is your max replica. Okay, and within each pod, you may have multiple containers. So one container may be related to vector database, retrieval from vector database. Another may be related to making a call to language model. Okay, so because these are independent processes, right? They run in separate containers. So things which are sort of interconnected, they can run in the same pod as different containers. Okay. Now these pods are running in something known as your cloud machine or instance or node. Okay, so think of a node as like a building with multiple floors. Okay, on each floor so there are 2 flats, right? So it has got 10 floors, and in each floor there are 2 flats, or 20 pods or 20 flats. Okay, and within each flat there may be 3 rooms. Okay, so you can think of that as like 3 different containers or 3 different things running, 3 different functions running. One retrieval, another is response generation. Okay, so and there can be multiple nodes. Okay, there can be one machine, there can be 2 EC2 instances, 3, depending on how you have provisioned your Kubernetes cluster. So that is what is cluster. The cluster may have multiple nodes. Nodes will have multiple pods, and one pod may have multiple containers inside it. So that is the general construct. Now, if you have to like sort of provision these pods, okay, and these containers, what you need to do is you'll have to first put the copy of the code, right, in each of the pod. So this copy of code that you put in each of the pods comes from the Docker image. So what is a Docker image? Do you understand that? Docker image. How many of you have heard about what Docker image terminology? क्या होता है Docker image में? मतलब बनाई है कभी, build की है? What all do you do? So you have a code package which has got say 3 Python files, okay, and one requirements.txt, all the dependencies. ये तो पता है ना requirements.txt, उसमें सारी dependencies है, ठीक है, with along with versions, ठीक है, and there may be some HTML code also for the front end, some CSS code, ठीक है. अब ये इतना code and some environment variables also, d.env file, ठीक है, and some config file also, some YAML file, ठीक है. अब ये जो है ये if you have this much, then what you can do, you can just do pip install requirements.txt in a new virtual environment. You start running your application. क्योंकि environment variables भी सब कुछ है तुम्हारे आपके पास, right? So this is like one independent entity, one unit, which you can, if you have this unit, you can run the code anywhere, because you also have the dependency and their version. So what people do is they package this as a Docker image. Okay. So now, and this Docker image will be stored in a Docker repository. This open Docker is there, Docker Hub is there. Then there is AWS ECR. Okay, so you can put Docker, create Docker images there as well. Now, as I was talking about, that we have to copy the code into these containers, right? So how do we do that? Okay, we have to copy the code of multiple files. Okay, then you have to put the all those things are to be copied here. Then things are to be installed, right? You have to run those pip install commands as well. So although, and then you have to define how many pods are going to be, minimum, maximum number of pods, right? Some scaling rules also you'll have to define that. Okay, if the CPU utilization exceeds say 90%, then I will sort of add some more pods, right? So that you do in the configuration files. Yeah, so that's what I have shown here. So all these YML files, they define your entire service. Okay. So generally there are 3 or 4 YML files. So one is values.yml, then there is one deployment.yml, and there is one namespace.yml. Generally these 3 YML files are there. Okay, they will define the configuration related to each container. Okay, and each container. So these are like 2 containers: Quadrant DB and VLLM inference engine. Okay, the ports. Okay, and so all these things. So for Prometheus, again, there is a separate image that needs to be pulled and deployed. Okay. For Quadrant, the image, Docker image needs to be pulled from here. The container name is ragvector.db. For embeddings, it will pull the embeddings from this ECR image, okay, or Docker image, and this will be the name of container. So you define for all the containers where all the code is actually going to come from, the images, okay, and some limits also you can put here, like in terms of how much memory it will consume, the vector quadrant vector database. Okay. So you define all those things here in YML files. And so for Grafana also, you can, Grafana I have not mentioned here. Yeah. So, yeah, so these are like your Prometheus targets. Okay, that the target is actually the VLLM inference engine, which is running on port 8000. Okay, this is another target which is quadrant vector database. So from here it will calculate, okay, like what is the retrieval time. Okay, here it will calculate, say, what is the time for first token or time per output token. Okay, and it will sort of scrape this every 5 seconds. So, and then it will get displayed to Grafana dashboard, okay, at 5 second intervals. So, in the afternoon, post lunch session, I will be giving you this entire code base. Okay, take a look at this. Okay, all the YML files, everything is self-contained in that, and we are going to be doing it in the lab. Okay, and because I have picked a 30 GB, 30 billion parameter model. Sorry, 8 billion parameter model, because we have RTX 4090 in the lab here. The 8 billion will be like 16 GB, and we have around 24 GB RAM. So yesterday I said that, like I tried to run it on one of the system, but now given like all the context that you all have, okay, so the exercise would be to sort of go to this link, okay, and just sort of fork this repo into your Git, in your personal Git, and then start using that code. Okay, so you can do it in your laptop if you want to do that. But Donald, we have some systems also, right? We have some GPU systems also, right? Yeah. So we'll do some practical work. So first, what we will do is we'll come to this class itself, try to fork it. We'll go through the code. I'll sort of give you a walk over the code. Okay, and then whatever, if you are able to run in some way in your system, try to run it. But then we'll go to the lab and try to host it over GPUs. Okay. So objective is to help you understand how do you sort of host it. Host an agent over Kubernetes service. Okay. So try to, so you have the link. So during the break, okay, just try to get this code in your, it's a public, visibility is public for this Git repo. So you can just fork it, and this is the folder of interest. Okay, it's Hyderabad. Okay, then we can take a break, lunch break now. Put the link in the chat. Right, so these are all the YAML files that we have. It's not readable, you know, on the screen there, but you can see it in your system, right? So the name of the files itself is self-explanatory. So the first file is the namespace.yaml. So it creates like a virtual partition within the node. So at the highest level, we have the cluster. Then within the cluster, there may be multiple nodes or multiple machines. And within the nodes, there may be multiple namespaces like dev, production. Okay. And these environments, okay, dev or production, is what you can specify here by specifying the namespace. Okay, and within that you would have pods, and within the pods you would have the containers, and within the container you would have like each service running. Say one related to retrieval, another related to generation. So this is the first file. I'm also uploading one more README into that folder. Can you see that readme.md in that folder now? In the Kubernetes folder, I have uploaded one README. Let's open that. No, I think it's in yeah, it's in the Kubernetes folder. Yeah. If you will fork the repo, no, means you will not have to download things again and again. I think it does an auto fetch. So first, so you would have the client, and then there will be ingress. Okay. Then it hits the RAG API, and the RAG API is divided into two parts. One is the vector database, quadrant, and the language model that you are serving using VLLM. So VLLM is a Python library, open source Python library. And under its hood, it packs all those things: page attention, flash attention, and it is used for serving the language model. So this namespace.yaml creates your virtual partition within your node. Then you have the secrets.yaml file. So you can store Hugging Face secrets here. Okay. Or if you are not calling a if you are like calling a language model API, you can store that as well here. Say OpenAI secrets. Then you have storage.yaml. Okay. Now, the purpose of this is it defines some persistent volume storage. Okay. One for the downloaded model weights and another for the quadrant vector storage. Okay. Then comes the VLLM deployment.yaml. So it will select the GPU node. Here it has been hard coded as RTX 4090. So that's the label that we have provided. And it will during the runtime, it will mount all the model weights from the storage HF cache PVC, and as well as it would have some empty directory also, which will be hidden. Okay, where all these operations, intermediate values will be there. Okay, and from it will also deploy this readiness or liveness probes. Okay. Then you have the VLLM service.yaml. So it is the one which sort of exposes the language model that we have hosted. Then we have quadrant deployment. So it exposes some of the ports, and it also has a readiness probe, which is ready YZ. Now RAG API deployment, it will capture, it will have some of these environment variable names. Okay. So for example, model name. Okay, like here we are going to use Qwen 3 8B instruct. Okay. For embeddings, we are using sentence transformer. If you are using BGE, then you can put that name here. Now top K, like how many chunks are we going to use? Hard coded as 4. You can change that as well. Now in the ingraph.yaml file, it has defined it has all those specifications for Nginx. Okay. And this is required to give HTTP, like give network access or HTTP access to this RAG API. Okay, and now these are the set of commands that you need to run in this order. So first you will one by one run these commands. Okay, and in this command you will also pass your Hugging Face token if you have not hard coded it there in one of the YAML files. Okay, so what this will do is it will sort of, so just like when you download a exe or DMG file into your MacBook or your Windows system, right? It installs all the things and then that application starts running. Similarly, here you are installing this application in whatever your laptop or whatever server by running these kubectl apply commands. Okay, so it will make that service ready and exposed. And of course, you can make changes to this. You can try using some other language model. You can have some other vector database in place of Concurrent. All that is up to you. Like it is sort of configurable. You need to change things here. And you will also see some values like here I have defined maximum utilization as 0.9. Okay, for GPU memory utilization maximum has been defined as 0.9 or 90%. Okay, for for the volume mounts, we have defined. So this is the volume mount from where we will be pulling the weights of the model. Okay, and we are saying that at most there will be like one GPU that will be running. Okay, and with an allocation of at least 16 GB memory. Okay, and for the different volumes, for example, for the weights, some size limits have been given. Okay, these are all the values that you can change actually, and these are all the metrics that we are going to capture: readiness probe, liveness probe. Okay, and for example, this will be measured every 20 seconds. This will be measured every 10 seconds. Okay, so and this is the ngraph.yaml file. So it is it is exposing it through Nginx, and here you can actually put, if you have really a domain that you have purchased, then you can hard code the domain here. Okay, so that on that domain your service will become available. Okay, otherwise it will just be the IP address of the machine. Okay, whichever machine you are running this service on. So that's the Kubernetes part. Let's look at the RAG API. So here is your app.py file. So this is like the entry point. It calls all those different functions. Right? All these different functions are called here. This is your system prompt is there. Then user prompt. Then this is where you're calling the language model. Okay, and then it will return the query response to the calling function. And all the dependencies are captured here. And anything that needs to be go in vector database, you can push it into this docs folder. This is a Docker file. Okay, so you need to build it, tag it, and then sort of push it. Okay, So build, tag, and push. These are the 3 steps. When you create a Docker, when you create and push a Docker image to the Docker hub. And this is the script for ingesting information into the vector database. Okay, it chunks the text, reads the information from txt or if it is HTML file, then chunks it. Okay, with the chunk size is 800 and chunk overlap is 100. Okay, so so one thing that you can untry is probably change the model name here. Means you can change the model name to something like Qwen 0.5b, which is a very small model. It will, even at like FP32, it will require only 2 GB of storage. Something that you can run on your laptop as well. Okay. If you want to do it on your laptop, this is the model that you can use. I'll share the name also. Okay, so this is the URL. So any questions on this entire code package? Okay. So how many of you are from coding background here who have written code in life? Please. You write code, run code. None of you? Means in your assignments also earlier, have you done any coding in the last 3 semesters? No, NLP में कोई भी webinars नहीं हुए थे? You've done coding? Right? Everybody? So can somebody help one of your colleagues? What is the difference between a .py and a .yaml file? .yaml files. YML, YAML. So his question is, what is the difference between .py and right configuration file? Okay. So you can talk to some of your friends because I don't want to go repeat things that have already been covered. Okay. And YML files are generally for defining configuration, right? So deployment related configuration you put in the YAML file, and of course Python is the choice of language for building your agent. Okay. And if you're building agents, also there are multiple libraries, open source libraries like LangChain, Llama Index. Those things are there, but they're good for proof of concept. If you're just building a demo prototype, it works fine. But when you really take them to production, they are very messy. Okay, you will not be able to optimize that agent. So people just do it natively, just write their own classes and functions and do it. Now, means if you all are ready, means you can try these tabs which are given in the README file on your system itself first. Okay, that will give you some confidence on how to do the setup of Kubernetes in your system. Okay, and yeah, probably after you have done some of these things on your own, we can then proceed to the lab. None of these are good. You write your own library. Production grade, none of the companies, like at least where I work, we don't use any of these. We built our own native libraries. That gives you more control, and then it is easy to sort of track where what is happening. Because some of the so the thing is, these libraries were created as open source projects by a group of few people, and then more people came on board and they started adding few more things. So there was never a proper structure to these things. So they have a lot of functionalities, but sometimes they are not compute optimized, sometimes they are not latency optimized. So they are not really very good, okay, when it comes to building anything for production. Okay, so just write your own library. It's not very difficult. So see, like if you are writing a library which is going to help you build a multi-agent system, what do you need? You need a way to call the language model. You need one function for that. Okay. You need a way to do the interactions between the agents. Okay, so you can create your own sort of MCP client and server in that, and you'll have to define some data types depending on what is being produced. If it is just text or if it is text and some metadata. Okay, and to ensure that the output is in a particular format, you can use a library like Pedantic. So you can build these things on your own from scratch. You don't have to really use these existing frameworks, because all these frameworks provide is just some abstraction, right? That okay, if you have to call these agents one after the other, what is an agent? It's just a function, right? So they say LangGraph says okay, that these are nodes that we are connecting. Each node is an agent, and then they say we are chaining the nodes. So there it will have a command, okay, langchain dot add node 1 2 3, something like that. It will chain, and then it says okay, compile the agent now, compile the multi-agent. So this is just an abstraction for making it easier for you to code. But what's really happening in the behind, like it is not very clear. And sometimes what happens is, say two agents are calling each other, and say one agent produces the wrong output. And in LangGraph, they are not really doing a telemetry around that. That okay, if the output of one of the agent or node was correct, now node 2 will agent 2 will get the input. Okay, now it may hallucinate, and finally you will see that the output that you're getting is not making sense. Now, how do you go and trace which agent or node was really malfunctioning? They don't really provide that level of telemetry, but you can do that, right? You can just write simple functions for each agent, and then you can do logging there. For each function call, you can do a logging. Okay, what was the input? What was the output? So more control and telemetry is possible when you do things in a native way. So I've created one more file, which is steps.md. Okay, now here all these commands. Okay, the first thing you will have to do is you'll have to if you are using like Linux or MacBook, I think these sudo commands will just be fine. Okay. For Windows, you'll have to have another equivalent of these commands, which is not there. But if you are on a Linux machine or on a MacBook, these commands should run. Okay, so step 1 is about some of the prerequisites. Okay, see if you have all these things installed. Okay, certificates, curl, ng, nupg. Okay, then you have to install Docker, and then check whether your Docker is installed properly or not. So, do you want to try this on your laptop, or should we go to the lab?
First we want to try it at our lab.
You want to try? So they want to try first. Okay, then how should you structure it? Like 30 minutes, they try it on their own, and then we go to the lab. So I'm here. Okay, if you are running into any questions, we can discuss. Not rendering very well, so you can look at this as well. Like it has got all the commands one by one. So you'll have to install some of the dependencies like related to Docker Hub, then NVIDIA, then Minikube, then kubectl. Okay, then you have to start the cluster. Okay, you have to label the nodes. Okay, then deploy by running these apply commands. You can probably come into groups of 3 or 4 so that you can try things together. Up to you all.
Folder.
So how are we doing in terms of trying things, installing? Yeah. Yeah. Right. Are you able to do that? Done. What about others? Is anybody sort of stuck anywhere? So, how many workers should we have? Okay, so that depends on how many cores do you have. Let's say your system has got 8 cores or 4 cores. Accordingly, you can have 4 workers. Okay, that is one. This was already covered. And the purpose of Nginx, I already covered this. If there are slow connections, okay, then it will buffer all the incoming payload. And when it has received all the incoming payload, it is complete. Then only it will pass on to the Python worker. Okay, it converts the HTTPS traffic into HTTP. Okay, and if there are sort of static elements of your website like HTML code and all that, which do not require any processing, then those things will be served from the CPU. So Nginx handles slow data pipelines, SSL termination, and monitors for any traffic spike. Okay, and enforces the like IP connection limits. Then is the UV-corn, okay, which will sort of load balance your work across different workers. Okay, and then the final thing, which is the core engine, where your VRAM is actually doing the running the language model and giving you back the response. When you're designing a system like this, you have to keep in mind some of the metrics. Okay, so this you all would be aware, so I'm going to skip. Okay, so regarding evaluation, you can use these frameworks like Ragas is one framework which measures context relevance, answer relevance, factual groundedness. These are some of the metrics it measures. Okay, so Ragas is also one of the open source libraries. It uses LLM as a judge for every response that is generated. And some of the metrics which are really important when you are hosting, self-hosting your language model: time to first token, time per output token. Okay, so time to first token, this is determined by the prefill phase. Okay, where your entire input, okay, whether 5,000, 10,000 tokens that you have given, its attention scores get calculated. And first is the prefill space. So if it is dividing your chunk into 10 different requests, then you'll have to wait for 10 iterations before you will get the first token. Okay, because the prefill will take at least 10 iterations, because in case the batch size is 500 and your request size is 5000, then it will convert it into 10 different batches. Once all those 10 batches are processed, then only the decoding will start. Then there is time per output token, which is the decode phase. So this is heavily dependent on how much is your KV cache. Okay, and again, concurrency is also limited by your KV cache. This I already explained. Okay, so if we would not really have the KV cache in place, then it will calculate those KV scores for all the previous tokens. Okay, but when we have KV cache, what we do is only for the token that is getting generated, we calculate the additional KV scores for that generated token, because all the previous tokens, the KV cache is already recording those scores. So this I also had covered that using phase detention, you are able to improve the utilization of your GPU RAM. Whereas in case of sort of reserved allocation, those small pockets of memory that could be left, okay, unutilized, may lead to underutilization of the GPU RAM.
Container tooling is also now. Container tooling.
So prefix caching and chunked prefill both are related to the prefill phase. And prefix caching is like you already stored some question answer pairs. And if a new query comes and that is similar to an existing or a previous question answer, it will just give you the answer from the prefix cache. So that reduces your time to for first token. Okay, and this chunked prefill is also it ensures that inter-token latency or TPOT for users for whom the decoding has already started does not get impacted. So it is always advisable to enable prefix caching, enable chunked prefill. Okay, all these things are sort of important. So if you want low latency, highly interactive agent, then you should not have maximum number of sequences more than 32, and the size of the batch, each batch should also be small. If you want an application which is high throughput, then you can increase the number of sequences and keep the batch size also large. Okay. So high throughput applications are like applications which will just run asynchronously, right? Suppose you just upload a job and it will keep running, and you will look at the job probably 4 hours later. Okay, things which can run in batches without real user interaction. Okay, but places where the agent have to be interactive, respond to the user, you need low latency. So better to have low maximum number of sequence and low small like total number of tokens in a batch. One is optimized for latency, another is optimized for high throughput. So just a recap of what we covered today. So we started with looking at how do we do quantization of model. Okay, then we looked at how after quantizing a model like Qwen 30B, how much space are we left with for the KB cache. Then we arrived at the concurrency using the number of by calculating the maximum number of tokens the KV cache can hold. Then we looked at quadrant vector database We also spoke about some of the observability metrics, which Prometheus is scraping, and Grafana is then plotting them over the dashboard. And in terms of serving, we need Nginx and GUnicorn to serve the application over HTTPS. Okay, so these are some of the numbers that you can keep in mind. Okay, like KV cache, then maximum number of concurrent sessions. Like if in case you are designing agent using this model, of course, quantize to int 4, then these are some of the choices you can make. Okay, and this will give you a time to first token of less than 0.8 seconds. Okay, so in terms of theory, like, yeah, that's all from my side. Okay, and yeah, if you all are done with your installation, then we can proceed to the lab. I was talking to Donald, like, because there are only few systems which have got GPUs. So all of you are here for, I think, 3 days, right? Till Wednesday you are here. So you can avail the lab, which with the WILP lab, and try things there in the systems which are Ubuntu based. You can run this steps.md. If you are not able to run it in your system, means then you can try running these steps in one of the systems which is there in the lab. They have got this 4090 GPU. Okay, and just see if you are able to deploy this. Okay, there will be one command. Okay, after which it will sort of show it is not moving anywhere. Yeah, so after this command, it will just show something like it will not exit. Okay, because what it is doing, it is just displaying things. So you can just do Control C. Okay, and then do the next step. Okay, then deploy the quadrant, then do all the remaining things. Okay. And this is how you sort of pass a curl request to do a query over the localhost over port 8080. Okay. So yeah, like that's all in terms of the theory. What is the time? Like we have another 90. So how do you plan to apply it? Like what you try to do? In your work, how will this be of relevance? Apply to AWS for time. Of course, it will not be able to support. But if your number of concurrent users is into 40 at any time, then I think this is good enough. Because there will be thousands of users, but not everybody will be chatting at it at the same time and all the time, right? So, yeah, this is like a sort of a production ready thing that we can try. And I have given the AWS instance also. So, if you are if AWS is a choice of a stack at Tata Motors, then yeah, this G64X large is what I had shown. Yeah, G6C4X large. And like I have more sessions actually which are available on YouTube. In case you want to look at do some deep dive around building AI agents and building verifiable AI agents. Then and like sort of building like do state management like memory. You can look at my sessions here. Okay, so this was a workshop that happened in one of the IITs. So all this is like I think 8-9 hours long. So you can look at that. In addition to this, I have also done a complete course on Agentic AI, which has 12 lectures. So all those lectures are also available here. Okay. I'm taking conversational AI next semester. Last semester I had to NLP.
Or any webinar.
I think, yeah, you can check the WL. You can, because I don't know if you can download and share.
Like you already have account with it.
So they will have to add you to their particular code.
Yeah.
Okay, so that you get the access to look at the code.
In any webinar, like
Webinar, I do like looking some of the faculty. So for NLP course itself, I think April, I did one webinar from the he was taking the second. So it was about like 8 rooms of building AI. It was actually one of my top at in like same I had done here actually. So that is one, and I have done 1 2 hour session on information retrieval for AI agents. Professor Ali Rai. So those recordings should be there. You can check those things.
and like you mentioned, this was 12 hours workload. So is there any glitch on
This was done at IIT Patna. So yeah, it is. But if you want something more than this, okay, like on weekends I do take classes. Like I have like some batch of 12 to 15 students. So yeah. So you can go look at the AIGurukul.dev website. Okay. The courses. Okay. And yeah, you can look at the course outline, and all those details like how to enroll are there in the course outline. And so we have some projects also, which, for example, this project right now around 25 students from BITS triple IT are working. These are all the students. In case you want to build something real life, well, these are like bachelors of engineering student. So every summer AIGurukul has an intake. We take around 25 to 30 students. Like AIGurukul have tie-ups with WITS and some triple ITs and IITs, so they send their students. Okay. And yeah, there is a team of mentors also, so they take care of it. But yeah, a lot of material is available here. You can just look at it and learn. Okay. Somebody was asking about prompt guardrails and all that. Okay, so these 2 sessions that I did with this person who works at Microsoft Redmond campus. So he's a senior security engineer with Microsoft, and he works in Microsoft AI. So you can look at these 2 podcasts, okay, related to prompt injection attack and indirect prompt injection attack. Yeah. So shall we go to the lab now? Or do you guys want? You all know where the lab is?